Hi, and welcome to 4.7.CW. That stands for classwork. Normal force, critical thinking. All right, in this one, in each of the following situations, I want you to draw a free body diagram and include all the forces on it. Find the weight, Fg. Write an equation for the net force to help you calculate the normal force, and then find the normal force. So, for number one, pretty straightforward. 5 kilogram book at rest on the floor. I don't know why the book is on the floor, but it is. You got to pick that book up and study from it. So you have the free body diagram, you got the weight pulling you down, and there's a normal force. The normal force is perpendicular to the surface. In this case, the surface is the floor. So part A, done. Free body diagram. Now we could calculate what the weight is. Weight is Fg, the force due to gravity. Fg is equal to m times g. Fg is equal to the mass, 5 kilograms, times the acceleration due to gravity, negative 9.8 meters per second squared. So the weight, Fg, is equal to negative 49 newtons going down. So mathematically, we represent the direction using a negative sign or a positive sign. On our free body diagram, if you wanted to write in the magnitude, you can. You don't have to write the negative sign here because the arrow is showing that the direction is downward. But you can if you'd like. Now the next step, C, says write an equation for the net force to help you calculate the normal force. Remember what net force is? Net force is just the sum of all the forces. That's what this sigma stands for, the sum of all the forces. So you just add all the forces together. Fg plus Fn. Now, this is kind of tricky. It's at rest on the floor. So you have to ask yourself, is this book accelerating? The answer is no, it is not accelerating. It has a constant velocity of 0 meters per second. Since it's not accelerating, that means that there is no net force acting on it. If we look at Newton's second law, it says the net force divided by the mass is equal to the acceleration. If the acceleration is 0, that means the net force must be 0. Okay, not on, but 0 newtons. So that's how we know that the net force is 0 newtons. The weight is 49 newtons down, negative 49, plus the normal force. So you add 49 newtons to both sides, and you get a normal force of positive 49 newtons. The math checks out. You get a positive number because it's going in the positive direction. Okay, very good. Number two, little trickier. We want to do the same process, though. You're pushing down with a force of 5 newtons on the 5 kilogram book at rest on the floor. So here's the box. Here's the weight of the book. So here's the book. Here's the weight of the book. What other forces are acting on this? Now you're pushing down with a force of 5 newtons. You could draw that here and call it Fa for applied force, but for this it might be easier to draw it here because you have the weight plus an additional applied force acting downward. I go F sub A to represent the applied force. You're applying a force downward. Now you have to ask yourself, am I pushing the book through the floor? You have to assume that you don't because it doesn't say that you're the Hulk. So you're not accelerating the book downward, which means that the net force is still 0, which means that the forces are balanced. So the normal force has to be equal to the sum of these two forces in order for the forces to be balanced. Let's write our net force equation again. We already know what the weight is, so we don't have to calculate it again. It didn't change. The net force is equal to the sum of all the forces. It doesn't matter what order you put these in because of the commutative property of addition, so you could just start plugging in what you know. The net force is 0 newtons again because you're not accelerating. You're at rest. You're looking for the normal force. The weight is 49 newtons downward, negative 49. The applied force is 5 newtons downward, negative 5. So if this is 49 and this is 5, what do you think the normal force is going to be? You have the normal force minus 54 newtons. So the normal force is equal to positive 54 newtons. Up. Very good. Okay. 3. You're pulling up with a force of 5 newtons on the 5 kilogram book at rest on the floor. Almost identical situation. One key difference. Now you're pulling upward with an applied force. And, maybe I should draw these vectors a little bit smaller. You want to draw the weight about the same size every time because the weight doesn't change. You have an applied force and the normal force, and the magnitude of both of those together, again, are balancing out the weight in the opposite direction. So I drew them smaller because the total should be equal to the weight. If that makes sense. You've got to balance out the forces because the net force is still 0. Okay, so the weight is still 49 newtons. The applied force is 5 newtons. We're looking for the normal force. The net force is equal to the sum of all the forces. You're at rest still, so the acceleration is 0, which means the net force is still 0. We're looking for the normal force. The applied force is 5 newtons up, positive 5. The weight is 49 newtons down, negative 49. You combine like terms. 5 plus negative 49 gives you a negative 44. The normal force is equal to 44 newtons. Note, in 2 and 3, the normal force was not equal to the weight. In 2, the normal force was greater than the weight because it had to counterbalance this additional applied force. In 3, the normal force was less than the weight because it was being helped out by this applied force. It didn't have to work as hard to balance out the weight. For number 4, it says you're pulling up with 5 newtons at an angle of 30 degrees with the horizontal. What the heck? Oh my gosh. All right, so you have the weight pulling down. You have some kind of normal force going up. And you have an applied force at some wonky angle. And it's 5 newtons. This thing is not even close to being at scale. But we got to draw it kind of bigger, because we have to break this thing into components, everybody's favorite activity. So why are we breaking this into components? There's a part of this applied force acting in the x direction, and there's a part of this force acting in the y direction. Since we're looking for the normal force, which is acting in the y direction, we are interested solely in the component of the applied force that is acting in the same direction, up and down, as the normal force. We don't really give a physics about what FAX is. Maybe if they asked what is the acceleration across the floor, we could find that and then use Newton's second law. But since we're just looking for the normal force, let's figure out what FAY is. Remember, this is just a right triangle. Here's your angle. Is FAY opposite, adjacent, or hypotenuse? That's right, it's opposite. How about FA? There's your hypotenuse. Opposite, hypotenuse. Let's use sine. FAY is equal to FA sine theta. That's the shortcut. You could do sine theta is equal to the opposite over hypotenuse, but it's the same thing every single time. We've been doing this since September. So you should know how to do this by now. If you don't, that's okay. Keep practicing. You can do it. All right, so FAY, I'm gonna go outside the box here, is equal to 2.5 newtons. That makes sense because sine 30 is 1/2. Okay, so 2.5 newtons are going up, and some other kind of newtons are going to the left, but we just care about 2.5 newtons. So let's do the net force. Net force in the y direction, you could even say, is equal to the normal plus FAY plus FG. Again, doesn't matter what order you put it in. It doesn't say that you lift the box up. It doesn't say you accelerate it in the y direction. So you can't assume that you're accelerating it. So since you're not accelerating in the y direction, the net force in the y direction must be 0. The normal force is what we're looking for. FAY is in the positive direction. We just calculated it. Good job. 2.5 newtons. The weight is acting downward. Did we change the weight? No. The mass of this thing is still the same. So this is negative 49 newtons. Again, it's going down. Don't just drop the negative out of nowhere. So 0 is equal to Fn minus 46.5 newtons. And then the normal force is going to be equal to positive 46.5 newtons when you add it to both sides. Okay. Now we're getting somewhere. Let's do number 5. It says accelerating upward at a rate of 2 meters per second squared in an elevator. It's the same book. All right, you want to accelerate upward at a rate of 2 meters per second squared. So here's your box. Here's your weight. The book still has weight. The weight is equal to 49 newtons still. Downward. Now, you're accelerating upward. So you're accelerating upward. Your net force has to be upward as well. That means these forces are not balanced. It also means the one that's acting upward is greater than the one that acts downward. This is the normal force. We know it's going to be greater than Fg, but what the heck is it? First, let's find out what this net force actually is. And we could use that. We could do that by using Newton's second law. F is equal to ma. So the net force is what we're looking for. The mass, what was the mass? 5 kilograms. And A is equal to, not negative 9.8. You're accelerating in this elevator upward at a rate of 2 meters per second squared. This is kilograms. This is meters per second squared. So the net force is equal to 10 newtons. Interesting. The net force is 10 newtons. Okay. Let's draw that. Let's write that net force equation again. The net force is equal to the sum of the forces, but now the net force is not 0 like it has been in the past. We're not at rest. We're not moving at a constant velocity. We're accelerating. We just calculated what the net force is. Let's plug it in. 10 is equal to Fn plus negative 49. I like to keep the plus sign just because net force, you're summing things together. You're finding the sum of the forces. And then when you plug in the value for the force, you say whether it's positive or negative, depending on the direction. So you end up adding 49 to both sides to solve for the normal force, and you get 59 newtons, positive 59 newtons. So mathematically, we can prove that, yes, indeed, the normal force is greater than the weight, causing this net force in the positive direction, causing you to accelerate upward. Number 6, similar, but it says you're accelerating downward at a rate of 2 meters per second squared. So here you draw your free body diagram. You got Fg, and if you're accelerating downward, your net force is down. So that means what happened to your normal force? Should the normal force be greater than, less than, or equal to the weight. That's right. If your net force is down, that means your weight must be greater than the normal force, or the normal force is less than the weight. Okay, so now we have to find out what this net force is. You could probably predict what it's going to be because we just did it on the previous one. It's just that the direction has changed. But we could plug in Newton's second law, F equals ma. The net force is what we're looking for. The mass is 5 kilograms. But the acceleration is 2 meters per second squared downward. Acceleration is also a vector. Direction matters. If it says downward, you better make that acceleration negative. That makes the net force negative, meaning the net force is down, negative 10 newtons. Mathematically, it makes a difference when you plug in, because the net force, again, it's equal to ma, but it's also, by definition, the sum of all the forces. If this is negative 10 newtons, then the normal force is what we're looking for. Oops. And you add, the weight is negative 49 newtons. So negative 10 plus 49 gives you a normal force of only 39 newtons. And if you look, that's less than the weight, just like we predicted. And we got a different answer for the normal force. Even though everything looked very similar, the fact that we made this negative changed the quantity of the normal force. The math checks out. If you're careful and you plug in a negative where you're supposed to, and you make numbers positive where they're supposed to, meaning you show the proper direction using a positive and negative sign, the math will work out. Have faith in positives and negatives, people. Number 7, moving up in an elevator at a constant speed of 2 meters per second. It's the same book. Now be careful. This looks similar, but what's different? What's different? Do I have to even tell you what's different? Come on, what's different about these two? This one's accelerating. This one's at a constant speed. Yeah, this is 2. Oh, Mr. Dangle, that's 2. It's got to be the same thing. It even says m/s. No, this is meters per second squared. Come on. It's different. It's a different situation. It's not the same thing. It's moving at a constant speed. So what does that tell you about the net force? What is the net force if you're moving at a constant speed? That's right. The net force is 0 again in this situation, 0 newtons, because the acceleration is 0 meters per second squared. Why is the acceleration 0 meters per second squared? Because it's a constant speed. This is important information. Anytime you see that, you want to underline it in the problem. They're telling you the acceleration is 0, which means the net force is 0. So even though you're moving, the forces are balanced. So when you write your free body diagram, Fg is all of a sudden going to be equal to the normal force again. Again, because the forces must be balanced, because the net force is 0, because the acceleration is 0, because you're moving at a constant speed. This is a good worksheet. 7 is a doozy, really. I mean, it looks simple, and actually it works out to be simple, but you have to know your stuff to really know what's going on. We already calculated the weight. It's 49 newtons down. What do you think the normal force is going to be? They're balanced. 49 newtons up. Just for physics and giggles, what's the net force equation? Just Fg plus Fn. Again, the net force is 0. Fg is negative 49. You're looking for the normal force. The normal force is indeed positive 49 newtons. Very good. Oh my gosh. Now we got a hill. All right, we're already at the 20-minute mark. I'm just going to keep rocking here. And let's do this problem. I'm going to try to do it pretty efficiently. It says the same book is at rest on a hill. The hill makes an angle of 30 degrees with the horizontal. It wants you to find the net for the normal force. So here is the hill. Here is the book. Actually, you know what? Let's try to make it pretty accurate. Here is the hill, more of a 30-degree angle. Here is the book. Here is the weight, FG. It acts straight down still. Make sure if you're doing this at home, make sure you write FG on the right side of the arrow, because we're about to draw some stuff on that side. Let me make the arrow bigger, because we're going to be drawing some crazy physics stuff right over there. The normal force acts perpendicular to the surface, not necessarily completely opposite the weight every time. Here's the surface, so we want the normal force to act perpendicular to the surface. I have no idea why my lines are getting so wonky, but they're pretty wonky. That's all right. So, okay, so the idea is normally we have an X and a Y axis. And in this case, the weight is on the Y axis. And now you have the normal force. And you have to break this guy into X and Y components. We've done all this stuff before. When you're on an inclined plane, like this one, when you're on an inclined plane, you don't want to put your X and Y axis like that. You want to put your X axis parallel to the inclined plane, and your Y axis is perpendicular to the inclined plane. And we do this because the normal force is aligned with this. And in the future, we're going to talk about friction, which acts parallel to the inclined plane. So even though right now it seems unnecessary, it's like, why don't we just do X and Y like we normally do? It's going to make it easier in the future because we'll have the force of friction and the normal force both on this new set of axes, and we'll only have to break the weight up instead of breaking the frictional force and the normal force up. It's just a little trick to make your life easier. Trust me, this makes it easier in the future. All right, let's get rid of this stuff. And here we go. We're going to break the weight into components that are parallel and perpendicular to the plane. So we want to write a right triangle, and what some of my students do, they'll just keep on making the line until they feel like, hey, there's a right triangle. No, 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 no. You don't draw it that far. You just draw it about this far, because this is the component of the weight that's perpendicular to the hill. You only draw it that far because now you have to start drawing the component of the weight that's parallel to the hill. Do you see how this component is parallel to the hill here? So that's kind of like the limit for how far you draw this guy. You can't just keep on drawing it on and on and on. Just like this video is going on and on and on. All right. Anyway, so the weight is still the same. What was it before? I even forgot that explanation took so long. That's all right. Hopefully you guys are learning something. If you're learning something, comment in the comment section. Say, I'm learning something. Or say, I'm not. Your videos are way too long. This is our 24 minutes. All right, let's see. So now you got to do some tricky geometry. If you know the angle between the inclined plane and the horizontal, they're actually telling you this angle too. And there's a proof that goes along with it. It has to do with alternate interior angles. Just something to remember that those angles are equal to each other. And now it's business as usual, believe it or not, even though it looks kind of wonky. You have a right triangle. FG is the hypotenuse. FG perpendicular is adjacent to this angle. So if you have adjacent and hypotenuse, you're going to use cosine. Yeah. Cosine theta is equal to FG perpendicular over FG, adjacent over hypotenuse. You could also write that as FG perpendicular is equal to FG cosine theta. And remember, FG is equal to MG. So FG perpendicular is equal to MG, FG, right, times cosine theta. So this is equal to, well, we already calculated that out. So this is 49 newtons times the cosine of 30 degrees. So FG perpendicular is actually equal to about 42 newtons. There's 42 newtons of force from this weight that's acting perpendicular to the hill. Now, there's a different amount of force that's acting down the hill, but we're not going to worry about that right now because we're just looking for the normal force. And yes, believe it or not, we're done. FG perpendicular balances out the normal force. Can you see that on the diagram? So you already know this is 42 newtons. If you wanted to make your net force equation like we've been doing, you could say net force in the perpendicular direction is equal to FG perpendicular plus Fn. The net force in the perpendicular direction is 0. You're not flying off the hill or going through it. In the perpendicular direction, you're not going anywhere. Maybe you're sliding down the hill, maybe not, but you're definitely not flying off the hill. So in the perpendicular direction, the net force is 0, and we calculated FG perpendicular to be 42 newtons. We could say it's down, negative, plus the normal force. So Fn is indeed 42 newtons in the opposite direction. Okay, this is probably my longest video to date. Have a good day.